day all, my name is Mrs. Nael and we are going to do Electrical Machines 3 in this semester. Electrical Machines 3 consists of 4 chapters, which are 3-phase transformers, synchronous machines, 3-phase induction machines, and single-phase machines. The chapter which is about 3-phase induction machines is a continuation from 3-phase induction machine that you have learned already in Machines 2, and it's going to be used as a GA assessment for this subject. So we are going to use that chapter to assess graduate attribute 4, which is investigations, experiments, and data analysis. The first chapter that we are going to cover is 3-phase transformers. I have sent you the study guide, the textbook, and also the modules or the notes already. So 3-phase transformers consists of 7 modules, and today I'm going to cover the first module, which is 3-phase transformers, core and winding construction. So here you can see the picture of a 3-phase transformer, and as you see here you have 3 phase which is going to be your high voltage side, and then you have 3 phase here which is connected to the bushes, which is a smaller which are smaller than this 3, and they are going to be the low voltage side. Then on top of the transformer here you can see the conservator tank, and then you can see 2 radiators which is on the both side of the transformer, and it's going to be used to cool the transformer. So inside the transformer we have windings, 3-phase winding, and then the oil will be there to work as a coolant and insulator. So the oil is the primary coolant of the transformer, but as we loading the transformer, because of the losses that we have inside the core, which are eddy current losses and hysteresis losses, and also the losses that we have due to the copper losses, the temperature of the oil will increase, and then we need the secondary coolant to cool the primary coolant, which is the oil, and as a result we have the radiators to cool down the oil and eventually to cool down the transformer. Now if we go to the next slide, again we can see the transformer, we can see the conservator tank, and then here you can see the breather, and then again the radiators. So why the transformer need a breather? The transformer has a breather because when load or ambient temperature changes, expansion and contraction of oil requires a breather which will not admit moisture. It works by sucking and blowing air from the conservator tank through drying agent, which is silicone gel, and a small sample of transformer oil. And we can maintain it by changing oil and silicone gel, and we usually need to maintain it when the silicone gel turns to pink. We can also see in this picture the oil level indicator, which is situated on the conservator tank, and we can see the oil filler hole at the top of conservator tank. Then on the next slide, again we can see inside the transformer, which you can see phase A, phase B, phase C. So here on phase A we have primary and secondary, phase B we have primary and secondary, phase C also we have primary and secondary. In the next slides you can see that we can have 2 different kind of the winding. In one of them the low voltage valve winding will be wounded inside, and the high voltage is going to be on top of that. And then we have also the pancake winding, which we going through it in the next slides. But here as you can see 3 cores of the 3-phase transformer. So 3-phase transformer can be made of 3 single-phase transformer where the windings are connected in star or delta in primary and secondary, or it can be a bank of 3-phase transformer as you see here. Again, this is another picture which is showing you 3-phase transformer. Again, you can see the 3 bushes, which is a high voltage side and the one from low voltage side. And what you see here, you see a fan. So in this case, you have a secondary coolant method, which is force, because if we have just the radiators and we don't have any fans or pumps, it means we don't have any force. But here we have also a secondary coolant, which we are cooling the radiator also with a fan. So later on, once we are going through the cooling method, you will see that we are going through 2 methods of cooling, which is natural cooling or forced cooling. And here we can see you have a fan, which means you are forcing the radiator to be cooled down. So just remember, once we are going through that chapter, that how the fan can be situated on the radiators of a 3-phase transformer. Now again, here we can see another picture of a 3-phase transformer. Again, you can see that you have 3 bushes here, which you connect the 3-phase, which is high voltage side to it, and then the low voltage side, the conservator tank, and then again you can see the breather, which you can have the silicone gel inside that, and then the oil will be injected here. Now this is another photo which is also showing you how the 3-phase transformer looks like. And again, inside the transformer here you can see you have 5 links. Again, in the next slides you see that you can have 3 links or 5, or a C core, and this is 5. 1, 2, 3, 4, 5. And here you have again 3 core, which means you have 3 limbs, and then you have primary and secondary bonded on top of each other, or it can be in the pancake method where you have primary and then secondary, primary and then secondary. Some of the transformers are very big, and you can compare it with the size of the person who is standing next to it. Again, here you can see the transformer from the outside and the people standing next to them. So this is another example of a 3-phase transformer, and you can see the conservator tank again on top of the transformer, 3 bushes, which is going to be connected to the high voltage side. On the other side you should have 3 bushes which is connected to the low voltage side, and usually they are smaller than the one for high voltage side. You can see the radiators as well. Again, here you have another example of 3-phase transformer, and you can see the radiators. You can see also the fan, which is there to cool down the radiator, and then you can see also inside the transformer. As we explained to you in electrical machines 2, the transformer has got a core, and the winding will be going to be wound around the core, and the core is made of laminated steel. Why we are laminating the core? Because we want to decrease the eddy current losses. So inside the core we have some losses, and the losses are hysteresis losses and eddy current losses. Hysteresis losses are caused by cyclical reversal of flux in the magnetic circuit, and eddy current losses are caused by eddy current circulating within steel induced by magnetic flux, and it can be controlled by reducing thickness of steel laminations, which is D, or thin insulating coating. Then we have the formulas for hysteresis losses and eddy current losses, and you can see that the hysteresis losses are proportional to the frequency and the flux density, and then we have a constant factor here, and eddy current losses also is proportional to the thickness of the steel laminations, also to the square of frequency and the flux density, and inversely proportional to the rho. So to reduce the eddy current losses, as we explained earlier, we can laminate the core, and also we should use high resistance steel to reduce eddy current losses. In the next slides, if you see the abbreviation HRS, it stands for high resistance steel, and we use it to reduce the eddy current losses. The disadvantage of the high resistance steel is the problem that we cannot cut it easily. And then we have also the abbreviation CROS in the next slides, and that stands for cold rolled oriented steel, and it's going to be used to reduce the hysteresis losses. And the problem with that is, or the disadvantage of that steel is the problem that it is expensive. So the properties of the core steel can influence the losses or core losses, and to improve the properties of the steel, we can do the following, which are use of CGO steel or tin coating with good mechanical properties, or improved chemistry of steel, improvement of orientation of grains, use of laser scrap and plasma irradiated steels, and continued reduction in thickness of laminations, or introduction of amorphous ribbon. In this slide, we can see BH curve of the different kind of the steels that we can use to make the core of a transformer. So BH curve is showing us how the flux density, which is the flux divided by area of the core, will be changed if we change the magnetic field strength, which is H. So as we increase the current in the winding of the transformer, then the flux which is going through the core is going to be increased. So as we increase the current, H is going to be increased, and as a result, the flux is going to increase. Therefore, the flux density is going to increase. But after some while, it's going to be saturated. Therefore, if you increase the current more, or if you increase the magnetic field strength, then the flux it cannot increase anymore. So the machine has gone to saturation. So you can see the best steel to use as a core is CROS steel, which is the one that I explained to you in the previous slide, which is cold rolled oriented steel, and it's there to reduce the hysteresis losses, because the machine that steel is going to saturation after the other steels. So what can we achieve from this BH curve? We can understand that if we have a transformer, let's say if it is 400 kilovolt ampere transformer, and if we increase the load to 500 kilovolt ampere, again, in that 500 kilovolt ampere, it might be able to operate. But if we increase the load to 550 kilovolt ampere, or even to 1000 kilovolt ampere, then the transformer cannot operate, because the core is saturated. And what we can get out of it is going to be losses, and the temperature of the core is going to be increased. But we won't get any induction out of that. That's why then the efficiency of the transformer would decrease. So what we can see from this BH curve, we can find the operation point of the steel. So in this slide also we can see the comparison of the magnetization curves for structural materials and transformer steels. Again, we can see different materials that we can use as the steel that we are making the core from that, and then we can see the BH curve for those kind of steels. And as I explained earlier, the CROS steel is the best out of all because it's going to be saturated at the latest stage. Now in the next slide, we can see how much power are you losing respect to flux direction. So as you see, the direction of rolling, it can be 0 degree, 45 degree, 90 degree. And then in the graph which we have here, we have core loss as we change the flux direction. And then we can find out how much power are we going to lose respect to the direction of the flux. On the next slide, also we can see the directional properties of CROS transformer steel, and also again we can see the power loss in watt per kilogram, how it's going to be changed if we change the magnetic induction of the transformer. Now, in this slide, we can see different type of the core construction which we can have inside the transformer. As you see here, the core construction can be in different methods. We can have a 3 limbs core type, which we have first, second, and the third limbs, or we can have 5 limbs. 1, 2, 3, 4, 5 limbs, and or we can have the C core construction. And then if we have 3 limb core type construction, then we have phase A, phase B, phase C on 3 limbs. And then if we have 5, then the first one and the last one, it doesn't have any winding on it. It's there only to make sure that the flux is going to be circulated, but the 3 limbs which is in the middle, they have winding on them. So and then we have phase A, phase B, phase C, and as you know, each phase has got high voltage side and low voltage side, or primary and secondary. So this part of the core where the winding is going to be wounded on top of them, it's called limb. And the part of the core which is joining the limb or is there for to make sure that the flux is going to circulate and going through the next one, it's called yoke. Again, you can see a transformer here, and then what we see from here, it's a bank of 3-phase transformer, and then we have phase A, phase B, phase C winding on that, and that's how it's going to be look like from outside. And then if we were having the fourth core in the middle, that one was going to carry the flux due to phase A, phase B, phase C, and because they are lagging each other in 120 degree from H3, you know that the sum of those flux would be 0. That's why we don't need that one in the middle, and that's how we have the windings. So we have phase A, phase B, phase C, and then in the next slides you will see how we are going to do the windings. Now again here you can see the core of a 3-phase transformer, and this is done with the simulation software, which we can see the name of that simulation software here at the bottom of the slide. Again, we can see 3-phase transformer here, and the same thing. So here we can see the limbs are steps to reduce mechanical and electrical stress on winding wrapped around them. So as you see here, we are laminating the core, but they are not all at the same size also, because we want to make sure that it's going to be more and more like a circle, or it would be round, so that once we are going to put the winding around it, the air gap between the winding and the core should be less. So That's why we don't make this lamination exactly with the same size, and it would be decreased as we come into the outer part to make it more like a circle shape. Again, we can see the construction of the three-phase transformer, and as you see at the end of the day, it's going to be more like a cylinder, and it's round. So for a given type and core shape, the relationship between core circle diameter, which is D, and volt ampere rating, which is S, is given as D is proportional to square root of S. For economic design, essential to restrict D by using as much as possible of core circle area. You will see that if we want to increase S, because the diameter is going to be increased by square of that amount, by some point, if increase S is fine, we can increase the dimension of the transformer. But at the later stage, sometimes we cannot increase S anymore, and instead of having a bigger transformer, we prefer to have another transformer in parallel to the first one. Now, in this slide, you can see the arrangement of high voltage and low voltage windings on the transformer. As I explained to you earlier, we can have two different methods of windings. One is the concentric winding. As you see, the winding of low voltage side is concentrated and it's in the inner part, and then the high voltage one, it will be on top of that. And then you can have also the sandwich or pancake winding, where you have the discs like you have for low voltage, and then you have the high voltage winding, again low voltage winding, high voltage winding, all of them again on the same core, but it's going to be in pancake or sandwich format. And then as you see, we have primary and secondary on the same core to make sure that the flux that is going through the primary is linking the secondary, and we are also reducing the leakage flux. And so here again is showing you how the winding is going to be bonded and how we are building the transformers. Again, the same thing happened here. The pattern of winding depends on rating and the voltage that we use the transformer for it. So we can have different kind of the transformer. We have distribution transformer, system transformer, transmission transformer, and the transformers is which is connected to generators, and then we are going to increase the voltage to send the power to transmission line. So if you have a distribution transformer, usually the rating is less than 1 megavolt ampere. The voltage of high voltage side will be 11 or 33 kilovolt, and the voltage of low voltage winding, which is the voltage that we can get in the consumer side, is 430 volt or 0.43 kilovolt. And this low voltage side, this is the voltage for three phase, and we can get a single phase out of that. And the type of the winding for distribution winding, it can be full or crossover or multi-layer, and for low voltage winding it can be helix. Then you can have system transformer. The rating is between 1 to 30 megavolt ampere. The voltage of high voltage winding is 33 to 66 kilovolts, and then the low voltage winding 11 kilovolt. The type of the winding for low voltage side will be disc or helix again, and the high voltage side is disc. And then again you have the transmission transformer and generator transformer, where you can see what's going to be the rating of those transformer and the voltage of high voltage side and low voltage side. and the type of the winding which is going to be used. So here you can see the different type of the windings that we can have, which is helix, disc helix, multi-layer helix, crossover, and disc. And these are the different kind of the windings that we can have. On the last slide, we can see the different kind of the conductors that we can use for our winding. So on the transformer. So the windings are formed from suitably insulated conductors. We can use the copper or we can use the aluminum. The copper is the one which it's used in most cases, and then you have the properties of each. Thank you.